Hi, so what I'm going to do is to take you through changes that we've already seen in the climate and the water systems in the West, the hydrology of the West. Then through projections, we'll spend a bit more time on the projections of global warming effects in the West. And then finally end up at the less certain future of precipitation in the West. So that's the structure of what we'll be talking about. So beginning with observations, this is actually a mix of observations and model. Let me see if I can wake up. No, you can't wake up the cursor. What I'm showing here, first of all, there's a black curve on here, a wiggly black curve that is the observations. Oh, thank you. It is the observations of global mean temperature during the 20th century. In back of it are two colored bands which correspond to the range of simulations that were done by Jerry Meal and people at the National Center for Atmospheric Research in 2004. They took a model and they adjusted parameters, adjusted initial conditions, and came up with sort of a range of what that model, how that model would respond to the climate forcings in the 20th century. With the blue band reflecting a bunch of simulations in which this global climate model is forced by volcanic aerosols getting into the atmosphere as they did historically, and variations in the brightness of the sun, the solar irradiance, as it did naturally during the 20th century. The yellow or the warm-colored band is all of that plus the effects of human emissions of greenhouse gases minus the effect of human emissions of aerosols, haze and smog and the like into the global atmosphere. And the upshot is that in the early part of the 20th century, the first two-thirds of the 20th century, you do slightly better, ever so slightly better, if you include both the natural forcings and the human forcings, although it's a statistical, I can tell you that statistically, your eyeball doesn't tell you that whether the blue or yellow are doing better, but at reproducing the observed trends. But by the last 30 years or so of the 20th century, we're in a new realm. And what we see is that with this model, you simply cannot reproduce the 20th century global temperatures without including the human effect. This work has been done by now by several more climate models from around the world, and it always reproduces this sort of result, so that we know it's not this particular model acted that way. It's the forcings. You really do need for the last 30 years to understand how climate has varied on a global scale. You need those human forcings. To bring it home to the western U.S., what I'm showing you here, the colored histogram back here is just the same global mean temperatures, again, now shown as a colored histogram. The wiggly blue curve in this case are the observed annual mean temperatures over the 11 western states in the lower 48 there, shown highlighted in white on the map in the background. And you can see that basically the story of global mean temperature rise and variations over the 20th century on these long time scales, we've seen very much the same thing reflected here in the western U.S. These are both being plotted on the same y-axis here. So we're seeing the same level of change in the western U.S. as we see in the global models at the global scale in response to the greenhouse gas emissions. And the rise, I should say, in this last 30-year period amounts to about half a degree C, or maybe a degree of Fahrenheit warmer over the last 30 years. So, and this slide is stolen from the IPCC fourth assessment that came out in February, and basically all it says, if you do the math on all these numbers down here, is about a half a degree warmer across the West. And that warming over the last 30 years we're already seeing its impacts on the water systems, the hydroclimatology of the West in a number of different ways. In each of these diagrams, red dots are sort of the indicating trends over the last usually 50 years in these studies that would go in the direction that you would expect from the in response to the warming. And blues are ones that are kind of fighting the trend. So up here, there's Noah Knowles and others have recently done a study that shows that over the last 50 years, there's been a trend towards having more of the precipitation that fall as rain and less of it fall as snow, in particular at all the red dots here. Over here, we've got the amount of snow on the ground as water content by April 1st each year over the last 50 years. Again, lots of red dots. Earlier stream flow, snow-fed stream flow, earlier snowmelt runoff down here. And this one, hopefully you can read that, is actually looking at plants. This is looking at a couple of networks of lilac bushes that were put out in the 50s, and they're greening up and blooming earlier. I should say, just to take these two down here, the average hastening of the snowmelt runoff over these 50 years amounts to about 10 days. You can nudge that this way and that by choosing which dots to look at and that sort of thing. But on average, it's about 10 days earlier now than it was in the 50s. These bushes, it's about 2 weeks earlier now than in the 50s.
Can you use the mouse to point it just a little?
I'm sorry.
Easier for
well, it doesn't wake up. Sorry, guys. Oh, fine, I did. God, this one's slow. Okay, sorry. Okay, am I making you crazy with the dot flying all over?
The camera can't catch it.
Oh, okay, sure. So just what does this look like? What does the stream flow impact of this look like? The big diagram here shows for the North Fork American, a river that comes down into Sacramento, the average annual hydrographs for the 1990s and for the 1950s in the two different colors here. And these are 2 decades that if you average the flows, the total amount of flow in those 2 decades was, very nearly equal. So this, what we're looking at here is almost strictly a timing shift in this diagram. In other words, the area underneath the 2 curves is virtually equal. And what we see, this trend towards earlier snowmelt, earlier runoff looks like is shown here, where we see this. In the 50s we had a good, healthy, we still have a fairly healthy April through July runoff volume, but the part of that historical April through July runoff is now showing up in the winter months. And it shows up in the winter months at a time when our reservoirs are being used in no small part in California to manage floods. And so during this period here, this runoff and the storms that bring this runoff it's sort of water as a hazard. During the gold bar here, it's water as a resource. And what we're seeing is a shift of water towards the winter when we really would rather it didn't come down. And the time series for the whole Sierra, not just the North Fork American, but the whole Sierra, of the fraction of the year's flow that comes down in that April through July golden period is shown down here in the corner. And it's been a decrease from, say, 50% of the flow coming off the Sierra in the April through July period back in the beginning of the century, 20th century, and down to about 40% now, and the trend continues. So those were the observations. Let's talk about what's projected in the future. On top here are greenhouse forcings, historical in black, and then a number of possibilities into the future in the colors and dashes. And I should note that if you look at the historical part of this, earlier I pointed out that the last 30 years you really need the human influence in order to understand what's happened to the climate. Why 30 years? We've been dumping greenhouse gases into the atmosphere at a hefty rate since the Industrial Revolution, and possibly for much longer than that since the Agricultural Revolution. But why 30 years? And the answer is up here. Because what we find is that following World War II, as economies started kicking in, and as a combination of the economies starting to kick back in and development proceed, and we started to throttle in the way that we dumped aerosols into the atmosphere, we reached a point in the 1970s where the greenhouse gas emissions started to really outstrip the effect of the background aerosols, and we see this rise such that there is an increasing trend in the first part of the 20th century. It's hard to see it on this diagram, but in the last 30 years, we've seen about that rate rise to about 8 times the rate of increase that it was in the first part of the 20th century. Into the future, we don't know how this is going to work out. We don't know whether we're going to get on a so-called a green pathway or onto a pedal to the metal sort of pathway. In any event, basically, if you take these various scenarios, run them through, in this case, half a dozen different climate models from all over the world under various of these emission scenarios that are basically talking about this cone of possibilities here. Just sort of lay them over each other, you get what I call a spaghetti diagram. That this is just sort of what the models project under, and trying to throw in the various uncertainties that have to do with models disagreeing with each other and with not knowing how our emissions will work out in the future. And the upshot is that at this point in time, for say Northern California, as shown here, as you can see here, about 20 out of 23 of the strands of spaghetti that I show up here end up within the range by the end of the 21st century of about, say, 3 to 6 degrees warmer over generally Northern California. It's a relatively narrow band, I think. But to kind of put what does that mean? What does in this case, 3 degrees warmer really mean to water in the West? Here what I'm showing is a little historical thought experiment. What I've done here is just take the historical record on a gridded historical record, the last 50 years, I should say, actually from 1950 to 99, and it's a daily record. And I went in and simply looked to see, historically, how many days were within 3 degrees below freezing to freezing. So in that just below freezing range. Remember that 3 degrees is down here on these projections. So this is a pretty conservative look at what the future could hold. I'd also note that when I think about 3 degrees, you can say, well, it's a very conservative projection in the scheme of things at the end of the 21st century, but it's also a temperature rise that you could see as early as, say, 2040 or something like that. So it may not be a matter of will we reach 3 degrees C, but when will we reach 3 degrees C. And anyhow, what I did here was to just take all those days that fell in that temperature range, just a little bit below freezing historically, and ask how much of the total precipitation fell on those days. And what you get is the pattern here on the national scale. And you can see that the blues are where there's relatively little or to no precipitation that falls in that range. The reds here are where as much as a third of the precipitation historically fell in that range. So this, like I said, this is just a thought experiment. What if things historically were 3 degrees warmer than they are now, or than they were historically? You could imagine, if you do that uniformly, that these are the kinds of days that would pop from being mostly snow to rain. So we could see an additional 30% here in parts of the Sierra Nevada of our precipitation falling as rain rather than snow. This isn't saying we get up to 30% of our precipitation falling as snow. This is additional. This is on top of the rain we already see. And you'll see, basically, this was an experiment in trying to determine where are the hot spots. And when you look on a national scale, the western mountains, that's our hot spots. And you look closer and you see the reds, it's the Cascades and the Sierra Nevada. So our Pacific Coast states are going to lead the way in the hydrologic responses to climate change, to warming in particular, especially in the context of this near freezing transition. This is a similar sort of thing, but now instead of adding up the precipitation, I just counted the number of days. And again, this is sort of a zeroth order model for you, but it's just historical data. You can do it on your own, your favorite weather series. And that's why I'm showing it. It's the simplest thing I can think of. This is, you might imagine, this has to do with how long the skiing season is, or the frozen season, the snowpack season is. And again, what we find, it's a bit more spread across the country, but we again find that the western states, the western mountains, are the ones vulnerable to this. And that's probably pretty obvious, but that's the way it works out. And again, the Sierra Nevada and Cascades are sort of the vanguard of this kind of change. So we gotta deal with it out here. Upshot is that if you take those kinds of changes and run them through a hydrologic model, down here, this is a detailed land surface model. This step up here is just little linear regression models, but you take these kind of numbers, take the most conservative, the coolest of the projections, and run them through various hydrologic models. And what you find, not unexpectedly from what I just showed you, is that there are major changes in the amount of snow that are on the ground and in the timing of runoff. So the big bright red, bloody, gory thing here is the changes in the Sierra Nevada by the middle of the century, where in much of the area you see reductions down to 10% of historical snowpack. In the high Sierra, in the southern part of the Sierra, they're high enough and cool enough that a few degrees warming don't actually unleash the flow, and so that you keep most of the snow. Now, a lot of the red here is places that maybe didn't have much snow to begin with, up here. And so this gory mess is a bit frightening, but when you integrate over the whole thing in order to sort of determine how much water are we talking about, we're basically talking about, by middle of the century, under a 2.5 degree warming scenario is what we're looking at in that one, about 30% less snowpack on the ground on your basic April 1st sort of thing. So coolest of scenarios find a major reduction in the natural storage that we in the state rely on. You take that to the whole west and look to see about stream flow timing, sort of up there. What you find is that by the end of the century, let's say down here where all the big red dots are, same temperature scenario, still only the coolest of the projections. We're talking about flows that typically will now be coming, taking the whole hydrograph and moved it a month earlier, basically. And, here's projected changes. This is changes in stream flow from the Sierra Nevada, western Sierra Nevada, more or less as a whole. And so what you see is this move of this to this amounts to that shift in the timing of the runoff and snowmelt and runoff. And what you end up with, probably not unexpectedly, is drier summer conditions because the snow isn't staying up there and then melting later in the year. It's coming down earlier. And wetter, more runoff in the winter time period. And I would just note that this is a simulated, these are simulated differences on a decadal scale. So take a whole decade, 20 years, and average to make a hydrograph historically, and then in this mid-century period, and then subtract the two. And even though these are 20-year averages that we're subtracting, you can still see the floods booming through this. So point is that this isn't just an orderly, okay, the flow's going to come down earlier. A lot of it is likely to come down as increased flood risk. And in the interest of time, I'll just note that when I play a game similar to the ones I showed you on the national scale with the same data set, I'm really not going to go into it much, but a similar sort of thing in order to try and pick out what areas are most likely to really be sensitive flood-wise to these warmings. I get this pattern, and the upshot is that the Sierra Nevada and Cascades, once again, we're the ones who are at risk of increased flood under warming. As I said earlier, the flip side of that is drier summer drier summer conditions in the rivers, lower flows in the soils and vegetation and the like, probably much drier, and so your wildfire risks look like they would be going up. Christina Tague is going to tell us more detail about how that ends up working, I think, the summer aspect of this. Okay, so this is a funny way, what happens to the growing season? This is a strictly temperature-based estimate of growing season. Or this is based on a strictly temperature-based measure of growing season length. And these are changes from our famous 3 degrees C warming. And again, once again, Pacific Coast states are the ones who are vulnerable to increasing length of growing season. And for some people that may be a good thing, but since there's only so much water around, it's not clear how that works out to be a good thing for us. Hold on, let's just pop along. I want to raise one more issue and before I turn quickly to precipitation. And that is just, we tend to think, we're conditioned to think in terms of groundwater is this cushion that water supplies in the West rely on during droughts and during bad times. You turn to the groundwater because what it does is the groundwater system gives this much muted version of the high frequency changes, the rapid changes that happen in precipitation or in stream flow and that sort of thing. Groundwater smooths it all out, and so you can always turn to groundwater. I would just propose to you guys, and this isn't something that I can document at all really at this point, but I would just propose to you guys that what we're talking about in terms of global change are trends. And that's really sort of the slowest way that you can change the climate. It's not bumps and wiggles. We're talking about a gradual trend on which bumps and wiggles will still reside. And so groundwater may actually be disproportionately sensitive to the trends that we're talking about. We're used to thinking about groundwater as the cushion against climate. It may be anything but that in terms of climate change. And for the West, this becomes particularly true. And that's because there's this growing mass of scientific literature out there that documents, and this is usually relatively recent stuff, that we're realizing more and more that Western groundwater is very much disproportionately derived from snowmelt. The way it happens is that if I just have rainstorms, 5 rainstorms, 12 rainstorms in a season, each of those has to try and make its way down and punch through the unsaturated zone and make recharge by itself. If I stack 5 or 12 storms worth of snow on the ground and now melt it in some some relatively rapid way, which is the typical way it melts once it starts melting. Now I'm punching all of those down together, and I get this, this greater recharge as a result. And so groundwater systems in the West are very much dependent on, in the long haul, on snowmelt. And of course, what are we expecting? Some of these large changes in response to warming? Snowmelt. Snow-covered area is likely to decline. The amount of snow that ends up in the snowpack, the number of storms essentially that get stacked in a given snowpack is likely to decline. And so recharge may very well be the part that's actually most at risk. And to show you that, let me just pop back here. This diagram here shows projections of change in total runoff plus recharge if you raise the temperature in a hydrologic model by 3 degrees C. If you look down here, we're mostly talking about the 5 to 10% range changes, okay? If we do the same thing but ask instead what happens to the recharge, what we're looking at typically here are 20 to say 35% changes. So, recharge may actually be at more risk than stream flow in the future. So, promised you precipitation. It's a water conference. You all think you need to know about precipitation. I'm telling you what we can tell you about is temperature, but let's talk about precipitation rapidly. Same sort of diagram as I showed you for temperatures. Forcings up top. Same 23 models down, or projections down here on the bottom. And this is for the same place, over in Northern California. I want to think about this more or less as Lassen. And the upshot is that what we find is that of these 23 projections, 19 of them are in the range that here it's shown as sort of centimeters, but let me tell you, this is the range of roughly plus and minus 5 to 10% change, okay? Closer to 5. So, your eye tends to get distracted by these couple that stick up out of the herd, but the consensus is for relatively small changes in precipitation, maybe a little bit wetter, maybe a little bit drier. Majority doesn't necessarily rule in this game, but it's trying to tell us something. And what it's trying to tell us about is if you look beyond Northern California and ask what's going on with precipitation in the projections, this is actually 13 models now, and this is from the IPCC fourth assessment. This is the most recent stuff. And under the one of those pedal to the metal Dick Cheney sort of scenarios, what I'm showing here, the colored areas are areas where over 90% of those 13, so basically between 12 or 13 of the 13 scenarios are all pointing in the same direction in terms of precipitation change. Blues for where they're all virtually, nearly all getting wetter. Red, pink, where they're nearly all getting drier. So you can see this broad area of blues up at higher latitudes, and a few places down in Mexico where you're seeing declines in precipitation. The heavy black curve here shows where half is sort of the place where half of the projections get wetter and half of them get drier. Okay, so even odds at those places. And you can see for Northern California, we're just sitting on that line. That's why it's not, but that line isn't sort of uniquely there. It's part of a pattern where it comes across the middle of the country. These dashed curves down here, are where the median mark what the median precipitation change amounts to in percents of historical normal. And what we see here, here, this one here is minus 10% change, okay? So in the most recent projections, in the ones that went into the IPCC fourth assessment that came out in February, if you look at the most extreme of the emission scenarios that they looked at, you find that this deep southwest, including Southern California, are sitting down there where half of the models are have lost fully 10% of their precipitation. So we see this pattern that the deep southwest getting drier. Really, yeah, a bit wetter along the northern tier of states, although we only see the 10 percentile or 10% change here. So most of this is less than 10% change, but they're consistently getting wetter. But for most of the country, we're sort of, or at least along the central part of the country, we're looking at, no consensus of which way it's going to go. And in fact, that's actually part of a bigger pattern. And the bigger the pattern gets, the more reliability or the more confidence we tend to have in terms of whether the climate model knows what the hell it's talking about. And so, this is just blowing out to the global scale. And what you find, here's our zero line again. That's the one we were looking at. And it's part of this broad pattern, but really a pattern that's the dividing line between the polar regions getting wetter. And there are good sort of first principle reasons why you would expect the polar regions to get wetter under increased greenhouse effect. The tropics getting wetter, but more importantly for us here in the west, polar regions getting wetter, and the subtropical desert belts here, the downward arm of the Hadley circulation, if that means anything to you, intensifying. And, Northern California and much of the west ends up sort of sandwiched in between the two. Okay? And upshot is that some of the models would have this blue wetter area maybe droop a little bit further south. Some of them would have the deserts maybe push a little bit further north. Right now, we don't have a consensus. This is what the black curve is where the median tosses up its hands and says 50-50. Okay? I would note, though, I look at this, and here I'm going to stick my neck out. Everything I've told you so far, I'm pretty comfortable with. But I look at this, and I say, well, if one of the things we know about California weather is that it's either wet or it's dry, and we don't see averages. And so one way of thinking about that, which isn't strictly climatologically true, down to the details, but is some years we might partake more of sort of the wetter kind of northwest kind of climate, and other years we may partake of more of sort of a drier southwest kind of climate. And so we get this fluctuation, this seesaw effect going back and forth, and El Nino is famous for sort of activating some of that. But more importantly is if that seesaw now is seesawing between stronger, wetter, even wetter northwest and even dry southwest, then we anticipate that even though the mean may not change, the average precipitation may not change, the excursions from year to year are likely to be intensified. Way down on a daily scale, if you dig into the model, drill down into the models, and look, here's downscaled projections from that coolest of the projections for a place over by Carson City, essentially my old hometown. This is an ugly picture, but it basically is a sort of ranking of how big various how often various large precipitation days occur historically and in the future model. And the upshot is that there's virtually no change in this on the daily scale until you get towards the least often exceeded rates, which is to say the largest storms get bigger. And this is in a model that shows effectively no change in the average precipitation as a result of all this. But the extremes go up. So, I don't know where I am on time, but there's the story. I've told you all of this, I believe. Warming by perhaps 2 to 6 degrees under current models. I haven't talked with you about the fact that this is likely to be even more so at higher altitudes. It is. Uncertain precipitation changes, maybe more, maybe less. Currently, for Northern California and for much of the West, outside of the deep Southwest, relatively small changes. in precipitation. And then a raft of hydrologic sorts of implications and changes that would result mostly, well, yeah, as I say down here, strictly in response to just the warming end, which we're comfortable is coming. We're not sure what the precipitation will do, as I've indicated for you. So.
MWD with respect to this energy-water
Sure.
partnership.
Thank you very much.
Thank you.
Thank you. I have to tell you, when I pulled into the guest parking lot today, they said, well, we welcome you here, but despite your license plate, which says USC, and though I received my doctorate from USC and taught there for many years, they taught me nothing about water. So any mistakes I make today, please do not blame that university. I am Tony Fellow, and I am first vice chair of the Metropolitan Water District of Southern California, and I'm very glad to be here today. And I see a lot of friendly faces and friends of Metropolitan. I think Dorothy Green was here. I don't know where she is now, but she is really the mother of water and power, and that's how we look at her. And in listening to some of the previous talks today, I think I come from a family that was a water and power family. My wife worked for Southern California Edison for a while, and I was in water politics. Now we've changed, we have almost the same hat. She's now head of media relations for the California State University system and spokesperson for Chancellor Charles Reed. And I work for Charles Reed as chair of one of the largest departments of communications in the United States at the second largest university in California. And I also was very interested in some of the previous talks, and I hope you asked me a question that was just asked about the governor's water bond measure, because I have my take on that, and be interesting to hear what you have to say also. The Metropolitan Water District of Southern California is very pleased to co-sponsor this event, the first Western Forum on Energy and Water Sustainability, and I'm pleased to be here on behalf of the chairman of the board, Timothy Brick, who I believe is in Chicago today. And I want to express our appreciation to the University of California at Santa Barbara and the School of Environmental Science and Management for launching this two-day forum. You have a great turnout, a great group of speakers, and it should provide much interest for you. The relationship between water and energy has a long history and is increasingly important. An often used quote, although we really don't know the source of this quote, or Met really doesn't know, and I don't know, said, "Water is for life and power for progress." And there's been an undeniable relationship between water and power. The truth is both are cornerstones of a vibrant and healthy society. A partnership between the two is perhaps the only way that progress can be made towards safeguarding the environment, natural resources, and the commitment to providing reliable service to Southern California. Partnerships are at the very core of the Metropolitan Water District, and our agency was formed as a consortium born in an era of cooperation in the late 1920s. A core group of cities in Southern California decided instead of competing with each other for water, they would join together. And the founding cities set a tone for cooperation that has more or less continued to this day. While there may sometimes be regional differences, and there is an underlying sense that we all are in this together to provide a safe and reliable supply of water to the people and communities of Southern California, for those of you who may not be familiar with Metropolitan, here's a brief overview. We are composed of 26 cities and water districts that provide drinking water to about 18 million people in Southern California, Los Angeles, Orange County, San Diego, Riverside, San Bernardino, and Ventura counties. And we're governed by a 37-member board of directors. It is California's second largest legislative body. And Metropolitan currently delivers an average of about 650 billion gallons a year, providing half of the region's annual demand. Metropolitan has, as many of you know, two main sources of supply, the Colorado River Aqueduct and the State Water Project. Additionally, the local resources projects are a growing source of local water for Metropolitan and its member agencies that are working collaboratively on this effort. And I'll talk a little bit more about that as we progress today. Along the Colorado River Aqueduct, there are about 240 miles of pipe and 5 pumping plants that require energy demands of about 300 megawatts to lift water about 1,600 feet. And Metropolitan has an allocation of about half of the water from the State Water Project, which is managed by the California Department of Water Resources. And we are located at the southern end of this project, and our water supplies have to traverse about numerous mountainous terrain. And we are very dependent on large amounts of electric power to make this water movement possible. We pay roughly about 70% of the energy required for the State Water Project, and this project also produces power from its hydro generation facilities. To give you a snapshot of Metropolitan's power cost, we spend about $200 million for transportation, $5 million for treatment, and Metropolitan brings in about $20 million in revenue for energy generated. In a California Energy Commission 2005 Integrated Energy Policy Report, it was calculated that the total water-related energy consumption is large, roughly about 19% of all electricity used in the state of California. In the wholesale market, Metropolitan acquires large amounts of power directly from its suppliers to be used on the Colorado River Aqueduct. Metropolitan also has an entitlement to power from Hoover and Parker dams, as well as some energy from hydro generation plants along the Colorado River. Metropolitan does have a long-term contract with the Southern California Edison, and this contract benefits both Southern California Edison and the Metropolitan Water District with the use of power and transmission lines owned by Metropolitan that connect Hoover and Parker to the Southern California Edison system. And during the periods when there is less demand for electric energy than we require for pumping, Metropolitan provides surplus energy to the Department of Water and Power to offset their power demands on the State Water Project. Metropolitan also, also has 16 small hydro generators, and all green. They're clean energy producers and located on its water distribution system. And the amount of energy produced at any one at all but one of these plants is dependent on water flows through pipelines. And all of this power is sold to Southern California Edison, the Department of Water Resources, and PG&E, thank you, at a specific contract rate. The other plant operates at off-stream reservoirs and is sold on the energy market. Similar to the electric power industry, we are a capital-intensive business. Our annual capital budget ranges from about $200 million to about $500 million per year. And our current long-term capital investment program has an overall budget of $1.84 billion. These capital projects, which include pipelines and pumping needs and the expansion and modification of treatment plants, all require an increasing supply of reliable power. And Metropolitan has a long history of implementing efficiency into our water treatment and delivery systems. And this includes specifying high energy monitors and lighting systems in the design of our facilities, installing variable frequency drivers for pump motors to reduce peak energy usage, installing energy management systems to better monitor and manage energy usage, modifying air conditioning systems at our facilities to improve efficiency, and conducting energy audits at our facilities with Southern California Edison staff to identify all possible opportunities for energy reduction. We know that conserving a unit of water reduces the amount of energy used to collect, treat, and deliver it, and it also saves on the treatment and disposal of wastewater. For these reasons, Metropolitan has a history of energy partnerships dating back to the construction of the Colorado River Aqueduct and its original mission. When the Colorado River Aqueduct was built, the hydropower generation at Hoover and Parker was utilized, and energy use was minimized through engineering with the incorporation of as few lifts as possible and efficient facility placement. And this attention to energy use continued with the building of the State Water Project, with the use of hydropower generation, energy minimization, through engineering and the harnessing of water at small hydro-generating plants in Southern California. Where we do see the issue of energy, where do we see the issues of water energy going? Over the next few years, Metropolitan's energy use is expected to increase as new drinking water treatment techniques are implemented to ensure compliance with drinking water regulations. And water treatment technologies have historically been a comparatively modest consumer of energy. Standard water treatment technology relies upon settlement and filtration to remove particles and chemicals, treatments for disinfection. And as new water quality regulations are implemented, energy-intensive technologies such as ozonization, membrane filtration, and ultraviolet light disinfection will require large amounts of energy. And so while we anticipate greater needs of energy, and we are also looking at ways to reduce the amount of energy we purchase in the meantime, a few of our capital projects aim to do just that. And they include the installation of a solar power generation facility at our Skinner water treatment plant in Winchester, California, as well as examining the feasibility of increasing Metropolitan's hydroelectric power generating capacity at existing and new locations on the distribution system. We also are monitoring wind power along the Colorado River Aqueduct and have already collected 2 years of data at this time. Solar power is another option at Metropolitan. We've been looking at solar power closely since 2002. Possibilities for its use in our system include the thin film on reservoir covers, roof and parking structures. A consultant study in 2006 presented a number of opportunities, and the first actual use will be at the Skinner Water Treatment Facility. This 1 megawatt solar facility will be mounted on the ground and require about 5 to 6 acres. It will produce 2 million kilowatt hours per year, and the treatment plant currently requires about 10 million kilowatt hours in which to operate. We're also furthering our development of our small hydro program, looking at the possibilities of adding additional units to this next year and reconfiguring an existing site and studying potential new sites. And what are the drivers behind this new momentum to harness greater efficiency, both in water and energy use? And the answer are many. They are first, an increasing population. Secondly, changing water treatment technologies that promise greater public health protection and aesthetic benefits. And they include ozone and the use of UV treatment technology. And finally, the acquisition of new sources of water, seawater, reduced water that require large amounts of energy to make potable. The answer to meeting many of these needs and demands lies not only in greater energy efficiency, but in water use efficiency as well. And the symbolic relationship of the two is most visible in our efforts to conserve water. For that reason, Metropolitan has invested significant resources and dollars in water conservation. Since 1990, Metropolitan has invested about $251 million across the entire spectrum of its water conservation programs, saving about 950,000 acre-feet of water. There are also new opportunities for co-funding of water conservation in recognition of its energy savings. Whether the water comes from a local well or imported over hundreds of miles, energy was used to produce it, and this present is a new opportunity to create energy efficiency through water conservation. Metropolitan also supports pursuing the energy savings opportunity and is currently working with the investor-owned energy utilities, the California Public Utilities Commission, to plan a pilot program funding water conservation through energy efficiency dollars. MWD also has proven to be a leader in the support of both new technologies as well as the implementation of innovative conservation programs, which has earned it a national recognition. Metropolitan has extended its focus on water savings to target businesses and commercial industries. In total, more than 80,000 devices have been retrofitted since the inception of Metropolitan's commercial, industrial, and institutional program in 1999. Many of Met's conservation activities fall under the umbrella of what we call the California Friendly Program, which was launched in 2006. In this past year, we undertook a major branding effort to extend the California Friendly nameplate to more products, organizations, and to programs. The California Friendly logo was fixed to homes as well as plants. The groundwork is being laid for a new California Friendly home certification program, as well as California Friendly programs for cities, schools, gardeners, and businesses. And Lewis Homes and other developers are now part of this California Friendly product. Water recycling, groundwater recovery, and saltwater desalination are viewed as growing assets in this region's water supply portfolio. The Local Resources Program continues to show steady growth with a 15% increase from fiscal year 2004-2005 to 2005-2006. While these programs add great value by diversifying the region's water resource mix, some also present substantial energy-saving opportunities. For instance, recycled water can use less than 25% of the energy of importing additional supplies from Northern California. And we should tell the governor that. And also, recent advances in energy recovery and membrane technologies have brought the energy consumption of seawater desalination to comparable levels with imported water supplies. Hand in hand with reliability comes sustainability. And Metropolitan has taken a number of steps to reduce our contribution to global warming, which you just heard about, and climate change. Both issues link water and energy together, as you heard today. From purchasing a new fleet of hybrid vehicles to studying expansion possibilities for hydropower, Metropolitan is committed to reducing its carbon footprint. Metropolitan has joined the California Climate Action Registry and is in the process of inventorying its greenhouse gas emissions in order to determine an accurate carbon footprint. Information from this effort will help Metropolitan determine emission reduction goals and a strategy to identify specific projects for the future. Activities and initiatives that will contribute to the state's overall goal of achieving an emission limit equivalent to levels in 1990. And to reach this goal, we're looking at the year 2020. Metropolitan remains very proactive in its efforts to be a good steward of the environment by continuing to pursue water conservation opportunities and initiatives, by reducing energy consumption and boosting production, and preparing its carbon footprint to identify emission reduction strategies. It would be impossible for Met to separate its water business from the business of energy. It would also be irresponsible. It may even be an arranged marriage of sorts if we look at it, but regardless of how these two resources have come together, it is incumbent on both to remain side by side and work on ways we can bolster both our resources and reliability, because there are too many people banking on the marriage to work out. The board and the staff of the Metropolitan Water District of Southern California look forward to continuing its partnership endeavors with our sister agencies, energy and power, sanitation districts, the business community, academia, and others to address our common goals and objectives. We all have an exciting window of opportunity to work together to do things a little differently, to integrate our programs and interest and balance the needs and interests of multiple stakeholders. And I appreciate being here today to give Met's message to you. The chairman would have liked to have been here to discuss this with you and other issues. And we hope to return next year to talk to you a little bit more about our progress in providing more water, yet reducing the energy to do that. So I thank you for listening to me today. Appreciate it.
Well, let's have a few questions.
Ask me about the governor's initiative. That's what I want to
Yeah,
talk
there you
about. So let me talk about it.
Go ahead.
At Met, we're undergoing this new goals that we have, and For many years in legislation, we always were waiting for legislators to introduce something in the state assembly or in Congress, and we've decided this year to take a different technique. The chairman basically has set a new direction that it's time for us to tell the state of California and the legislature what we want, because most of them don't know the first thing about water in Washington and in California. And so with this, we are now taking more of a harder stand on some things, and we're looking at this. We haven't supported the bond measure for a number of reasons. One is that we don't believe we need more reservoirs in Northern California. For one thing, what we need to do is to concentrate on Southern California. And one of the things we need to do is to clean up some of our wells. As you know, Southern California has been struck with perchlorate, chromium-6, and if we could get some money in that bond issue to rapidly clean up some of our wells, we would have more groundwater storage. In addition to that, I come from a district, the Upper San Gabriel Valley Municipal Water District, which has perhaps the best groundwater in the state of California. It's huge, but half of our wells, 400, are closed because of various VOCs and other chemicals in the water. And we need more money to clean these up so that we can store more water, and along with that, to really push our recycle programs in Southern California. We now believe, particularly with my agency, which has been one of the forerunners of recycled water, and Bill Clinton called it the model project in the nation when he gave us $25 million, and we're now in our third phase. But we need to plan more recycled water, clean up the basin, and none of this is in the governor's plan. And so if you have any input, and we're trying to get it, we've called our legislators, our Southern California legislators together, and we're trying to get them to get to the governor that perhaps we need to look at this before it gets to the ballot to provide some money to do this in Southern California, and I think we'll all be better off. But we do not need more reservoirs in Northern California.
Could you follow on that with a comment on groundwater recharge potential in the basin, one you're familiar with, and also Santa Ana?
I know we have many, go ahead.
So the question is, what's the groundwater recharge potential?
There's many of you in here from the San Gabriel or have worked in the San Gabriel Valley, probably know more than I do about this, but I think we have tremendous potential. Right now, my general manager, Tim Yoakum, we had a talk this week because I've been really pushing for more groundwater storage because Met has, and we have a partnership with Metropolitan, and it's less expensive than building reservoirs. Our last reservoir was Diamond Valley Lake, which came in under cost, but it was tremendously expensive, and we don't have the money. Our general manager, if he was here today, would say we would not pursue any more reservoirs at this time. But I think there's tremendous potential. But my general manager, as I said, has talked to me this week as I'm pushing this groundwater recharge thing, and is telling me we've really got to push recycled water, that would be the best benefit right now in California, Southern California.
Going to be Tom Feely from the National Energy Technology Lab for the Department of Energy, and he's going to give us a perspective on freshwater needs over the coming few decades for thermoelectric generation. So, Tom?
Thank you, Arturo. I think I have about 6 minutes to do a 25-minute presentation.
Go ahead, take your time, and then we'll just...
And I'm the only thing that stands between you and lunch. I'm also going to talk about what's probably considered a four-letter word in the state of California, and that's coal. So forgive me telling you that in advance. What I'd like to do is talk about some analysis that the Department of Energy's Office of Fossil Energy, specifically the National Energy Technology Lab, conducted over the last couple of years. And these analyses were to look at future freshwater withdrawal and consumption by thermoelectric generation, both current and projected increases in thermoelectric power generation. So I'm going to provide a little bit of background information that relates to the linkage between thermoelectric power plants and water. Talk about the analysis we did sort of projecting into the future. I want to talk a little bit about a research and development, technology research and development program that we initiated to address these issues of perhaps better managing or reducing the footprint that thermoelectric power generation has on water. And then what we did next is to look at that R&D that we're carrying out and try to project into the future if some of that R&D were to become commercially successful and was deployed over the next 25 to 30 years, what potential benefit would be gained by the deployment of that advanced technology. A little bit of background. I thought some of the speakers prior to me would maybe have covered some of this, and I thought I could go through some of these slides a little quicker, but I'll slow it down a bit. Two key points from this slide. The pie chart on the upper left side is and it might be difficult to read, but the bottom line is thermoelectric power generation is the second largest withdrawer, if that's a word, of fresh water in the United States, just slightly behind irrigation agriculture. If you look down at the lower right, that's withdrawal, freshwater withdrawal. Down in the lower right is freshwater consumption. You can see that for thermoelectric power generation, most of the water that is withdrawn is returned back to the source. And that's a point that's oftentimes lost in the discussion about thermoelectric power plants, whether they're nuclear, natural gas, oil, biomass, coal, is that most of the water that is withdrawn, and most of that water is withdrawn for cooling, is returned back to the source. The other key point, takeaway from this slide, is we're beginning to see more and more the question of who gets the water. In California, that's a real issue. Thermoelectric power plants are in line or in the queue with domestic use, in-stream use, agriculture, et cetera, et cetera, et cetera, et cetera. So the question is, who's going to get that water? The next slide is, we've been collecting, when I say we, the DOE, and DOE, the National Energy Technology Laboratory, is part of a larger national lab effort that's been looking at the linkage between energy and water, and that also includes EPRI. But we have seen in the recent, just the last couple of years, conflicts arising between who gets the water. And oftentimes, power generation, whether it's hydro or thermoelectric, is coming out at the end of the line. In other words, when you ask the question, who's getting the water, oftentimes power plants are not. So these are just headlines taken from various publications over the last year or so. And water has become such an issue with the thermoelectric generating industry is that Power magazine, about a year ago, in May of 2006, dedicated an issue just to how to design a thermoelectric power plant, a steam power plant, to conserve water. So it's becoming a more and more crucial issue. In collecting those headlines, those stories, we wanted to be able to maybe quantify what those headlines meant in terms of impacts on thermoelectric power generation. And so we went and looked at all those stories and articles over the last 2 or 3 years and put together this table. And again, those articles primarily deal with issues between thermoelectric generation, but there's other sources like hydro that are being impacted by water, lack of water resources or competition for water resources. And what we calculated, and again, this is a rough estimate, this may be 30–40% plus or minus, but about 35, close to 36 gigawatts of capacity has either not been built or has been taken offline temporarily due to drought, low water conditions, high water, high river temperatures over the past couple years. So it's a real issue. It's not just headlines, it's actually gigawatts of electricity either, again, not being built because a power plant cannot get the permit that it needs for the water for cooling, or that hydro or thermoelectric plants had to reduce output due to, again, periods of low flow. Okay, the analysis I referred to was, we did it initially in 2005 on a national basis. And just this past year, in 2006, we wanted to update that analysis, and we looked at it again nationally from the standpoint of the Energy Information Agency projects energy demand or capacity out through 2030. So we took the EIA data, and we looked at it both, again, nationally, and we also looked at it on the 13 electric generating or grid regions in the United States. And for this presentation, since it's the Western Energy Water Forum, we'll focus on the Western energy regions, particularly 3 subregions, the Northwest Power Pool, the California subregion, and the Rocky Mountain subregion. What this slide is showing between 2005 and 2030, in all 3 regions, we're expecting to see growth in population. I think if you look at California, that 29% matched up pretty well with what Ann spoke about this morning. I think her number was around 28% through 2025. But we're expecting to see increases both in the demand for electricity as well as population growth. So you take population growth and that population wanting electricity, you bring those two together and you have the potential conflicts. And so one of the questions we wanted to know is, okay, we have these projections on thermoelectric energy demand. The Census Bureau gives us projections on population growth. What does this mean in terms of if you meet that demand through thermoelectric generating capacity, what does this mean in terms of future impacts on freshwater consumption and withdrawal? And I'll start to get into that a bit. We looked at that. We looked at 5 cases or scenarios. Let me just hit this. In our analysis. And the one that I'm going to talk about today is what we call the regulatory-driven case. So we looked out in the future. EIA, again, projects new demand coming online, new thermoelectric power plants being built. EIA also projects plants being retired. So in the case of the regulatory-driven case, we assume that all additions use fresh water, and they'll be equipped with wet recirculating cooling systems, while all retirements that EIA projects are proportional to current water source and type of cooling. And there are 4 other cases that are included in a paper that we did if you're interested in seeing what the results of those other cases are. Okay, on a national basis, this slide shows what our projections are in terms of changes in withdrawal of fresh water between 2005 and 2030 based on EIA's projection of thermoelectric generating capacity, new units plus retirement of some older units. And our projection is we expect to see about an 8.6% decrease in the withdrawal of fresh water to meet the increased demand for electricity. And that may seem counterintuitive. The primary reason we see that is that the retirement of older plants, many of those older plants are once through. So you're taking offline once through plants that use orders of magnitude more water than a closed-loop cooling plant. So intuitively, if you're thinking, well, more demand, how could you have a reduction in withdrawal? And that's the primary reason is you're going to see a retirement, at least our projection or assumption is that you're going to see a retirement of older once-through plants that withdraw a lot more water. Now let's look at it from a consumption standpoint, From a consumption standpoint nationwide, we expect to see an increase, about 32.5% increase nationwide in freshwater consumption. Now keep in mind that that sounds like that could be a critical issue, and in fact it might be in certain regions, certain states. But going back to that pie chart on the lower right, thermoelectric power plants currently consume only about 10% of what irrigation consumes. So although it is an increase, it's an increase in a small amount of consumption. But again, that could be an issue from a regional or state perspective. But again, the reason that withdrawal is, we project withdrawal to be reduced is the retirement of once-through plants and the fact that you're bringing online more closed-loop or recirculating cooling systems tend to have a higher consumptive footprint than once through, and that's why we expect to see an increase in consumption. All right, let's look at this regionally from the 3 NERC regions that we showed earlier on that map. And let me just tilt this. I got it. It won't tilt. All right, I'll just move over. As we can see here, we expect to see about a 3% decrease in the California region in terms of withdrawal. The Northwest power pool, there's actually expected to be a somewhat, about a 32% increase in withdrawal in that region, and then again a decrease in the Rocky Mountain region. And these increases and decreases are all based upon both the EIA projections of retirements and additions of new thermal coal capacity and some assumptions that DOE made in terms of what we came up with a number of model plants, and we assumed that certain types of plants, thermoelectric plants, would go in certain regions of the United States. So you'll see overall we expect the withdrawals in the United States to decrease, but regionally there are some exceptions to that. And the report goes into much more detail on how we arrived at these numbers. Consumption. For all three regions, we expect to see, again, consumption to increase. Again, this is based on a retirement of once through, and any new capacity coming online would be closed loop. And this case 2 scenario that we're talking about here is business as usual. In other words, it is EIA's scenario in which there is not a carbon-constrained world, and these numbers could change drastically if we see CO2 type of regulations on thermoelectric power plants, and you'd see a movement perhaps quite a bit away from coal-based and other fossil-based steam generating units. And we also assumed in case 2 that all the new plants coming online would be wet recirc. Now, we did not assume any dry cooling coming online, and that's a little bit of a risky assumption because we probably will see more dry cooling coming online. So if we saw more dry cooling, both the withdrawal and the consumption numbers would come down. You see less of an impact. Particularly in the West where you can't get the water, you're likely to see situations where dry cooling or air-cooled systems would be used in lieu of wet-cooled. All right, this slide just summarizes the results for the three regions in terms of increases in generating capacity and impacts on freshwater withdrawal and freshwater consumption. And I'll make this presentation. I don't know if Arturo is planning to make the presentation materials available, but certainly you can give me a card and I can send them to you because I see people trying to take notes. We'll make sure you get the information. All right. This is a flow sheet that kind of lays out a thermoelectric generating plant. You're burning fuel to produce heat. Heat produces steam. Steam drives a turbine. You need to condense that steam back. You use water to condense the steam, and hence the need for water for cooling. It's for cooling of the steam coming out, the low temperature steam coming out of the turbine. And this kind of moved kind of quickly, but what I wanted to point out is that the primary places of water loss in a power plant are out the cooling tower stack. That's the major consumptive loss. But you also have loss out of the stack gases or out from the flue gas. And you also have blowdown, depending on the number of concentrations, cycles of concentrations you have around your cooling system. But the major loss is evaporative loss out of your cooling tower. Now, DOE, NETO, we initiated research and development of technology to reduce or better manage how power plants, thermoelectric power plants, use water. And these categories are sort of a generic description of where we're doing research. We're doing research, if I go to the next slide, it gives you a little bit more detail. We've lumped the research into 5 categories, and this provides a short summary, but basically we're looking to reduce the evaporative loss by looking at advanced cooling technologies. One of the areas that has a lot of promise, and it's come up here in California, and that's using impaired waters in lieu of fresh water in a cooling cycle, whether that's industrial wastewater, whether that's produced water from oil and gas extraction, and in the east we've looked at using underground coal mine water in lieu of fresh water. Looking to increase the cycles of concentration around a cooling tower so you have less blowdown. You can run that water through more times before you have to blow down. That's an opportunity to reduce water loss. And there's a fair amount of moisture in the flue gas from a coal-fired power plant. And we're looking at some technologies that could recover and reuse that water. You could get 15–20% of the water you need to run your recirc cooling tower if you can recover water from the flue gas. And then the final approach is to look at cold drying. And that takes a little thought, but the idea is to take the hot water that's returning to the cooling tower and run that through a heat exchanger to dry high moisture coals. So you're going to recover moisture from the coal and use that. You're also going to reduce the temperature of the hot water returning to the cooling tower, and you may be able to reduce some of the evaporative loss because the water going to the cooling tower is a little bit cooler than it would normally be. All right, so why am I telling you all this? Before I get there, I put this slide in here, but I probably don't have a whole lot of time to talk about it. I'll just say that we do have metrics that we establish for ourselves. In terms of doing this R&D, we measure ourselves against performance and cost goals, and we've established long-term and short-term cost goals and performance targets for our power plant R&D. And given the lack of time, this slide, I could probably spend about 15 minutes explaining how we got to it. But we use air-cooled system as our baseline. That's your best technology. If you don't want to use water, essentially don't want to use water in a thermoelectric power generation plant, you go to air-cooled, dry cooling. But that has an energy penalty, it has a cost penalty. And so we did some calculations to come up with our performance and our cost targets. I'd be happy to talk to somebody offline about that at lunch or afterwards. Okay. What we did next, I had mentioned that we did the analysis initially to look at projections of freshwater withdrawal and consumption impacts by meeting the EIS projections for new capacity. We wanted then also to look at, so if DOE was successful working with contractors in developing some of these advanced R&D technologies and we deployed those technologies, what kind of impact could that have on perhaps reducing freshwater withdrawal and freshwater consumption? And so we looked at each of those 4 or 5 categories individually, and then we also grouped them together. In other words, what if we use underground coal mine water in lieu of fresh water at a power plant? That would be one case. What if we did that plus coal drying plus advanced cooling technologies? So we bundled, in some cases, all 5 of the categories of technologies together. And what this shows you, and this is for the WEC region of Western Electric Coordinating Council region, which includes those 3 subregions. The dark orange colored bar is the baseline, in this case, withdrawal. And then for each of those technologies, if they were commercially deployed, and we assume 50% commercial deployment. So we were successful in the R&D, and 50% of the thermoelectric power plants use these technologies. What these bars are meant to show is what the impact would have on reducing freshwater withdrawal for the WEC region. And we have a series of these, and again, in terms of saving some time, let me just go to the California one. And the shape of these bars are about the same. You would expect to see, if you go all the way to the far right, if you combine all 4 technologies, or excuse me, 5 categories of technologies on a new power plant, you could achieve fairly significant reductions in freshwater withdrawal. Okay, let me just move over to California in terms of consumption, since we're in California. We did the same thing. We assumed 50% deployment in 2030. The dark blue is what consumption would be in those 3 regions, or excuse me, in the California region in 2030, and what would happen if we were successful in developing the technology and it was actually commercially deployed. We'd see these changes in terms of freshwater consumption. I think the next, let me just run through these. Next slide is an attempt to summarize those 8 previous slides. It shows the WEC region and then the 3 subregions, reductions in withdrawal, reductions in consumption. Again, if we were able to be successful, if we were successful in the R&D and the private sector then decided to deploy those technologies. And we converted this to acre feet. I'm not used to thinking in terms of acre feet in the east, but certainly that's the way you guys look at water in the west, so we moved that over to acre feet. So you can see there's a potential for some substantial decreases in both withdrawal and consumption by doing R&D. So I guess I'm kind of standing here promoting the need for research and development in this area. And I think I'm representative of the other national labs that are part of the energy water nexus and trying to push forward a program that would increase in the government funding of research directed at the linkage between water and energy. Summary. My last slide. How much time do I have left? Can I take 15 minutes on this? All right, I'll just read through this. I went through the slides fairly quickly. So I guess some of the critical points. I won't read through this, and I'll just try to summarize the points I would like to get across. Obviously, there is a strong link between this segment of energy, and that is the thermoelectric power generation. You need water if you're going to go with wet cooling, and that's the largest need for water in a thermoelectric plant, whether, again, if it's nuclear, coal, oil, natural gas. We expect to see a decrease overall nationwide in withdrawal to meet thermoelectric power generation demand that's projected by EIA. We would expect to see about a 30% increase in consumption. But again, keep that consumption in mind. It's relative to say irrigation. Even at a 32% increase in consumption by thermoelectric power generation, that's less than 10% of what irrigation agriculture consumes in terms of fresh water. As we see, particularly in the West, not just California, well, not just the West, the Southeast, we're seeing population growth. We're seeing conflicts between water and power production in the Southeast, in and around Atlanta, Georgia. But as you have increases in population in regions where water is scarce or where there are a lot of competing needs for that water, there is a potential for electricity generation sector to sort of get pushed to the back of the line. So in response, NETL, as well as the other national labs and EPRI, are working on some R&D to, at least from the standpoint of power plants, to reduce or better manage freshwater use. We're going to continue to update this analysis. Our next update, we really want to take a look at a carbon-constrained world, and we didn't do that in this one. So that obviously would could potentially have would make a lot of changes in some of the numbers that we project. And with that, I'd be happy to answer any questions you have.
Yes, a question?
Yeah, I'm Chris Scott from the University of Arizona. I have a question with cooling use of impaired waters, and particularly what impact on salinity levels you expect by using impaired quality waters for cooling. In other words, does the evaporative process for the cooling concentrate salts, and then what are the either environmental discharge requirements that you need to comply with for that, or subsequent cost penalties for desal that water?
So the question is, what are the implications of using impaired waters for cooling systems?
Yeah. They're all very good questions. I don't know that I have the answers for them. If you're going to use a producer-impaired water in a cooling plant, there are water quality requirements to deal with or prevent things like fouling, slagging, corrosion. So you would likely treat that water before you use it at the plant. The salts, et cetera, that would be removed would have to be dealt with in the appropriate manner. I don't know that we had a project with EPRI to look at actually using produced water, treating it and using produced water at the San Juan generating station. We do have a report on that. So we've run some economics on that as an option for at least reducing some of the freshwater withdrawal demands on the San Juan River. I can hook you up on that report.
I'm Ari Bachrock from Ensor. How do you see the use of reclaimed water coming out of municipal wastewater treatment plants and in trends and increasing? That's something that's getting proposed more in California.
Yeah, I think we've seen some of that happening in New Jersey and other places. You know, a lot of this application of these novel concepts or new technologies are oftentimes you require a regulation for them to happen. The utility industry may not adopt them if they can still get fresh water from the river essentially free. So I think as we see more and more conflicts between water users and the need for power in a certain region, then hard decisions are going to have to be made, and you may see more and more reclaimed water being used because that's the only option that's available. Either that or you go to a dry cooling system. So it's going to be an economic decision. It's probably going to be driven a lot by regulation.
So the question was the use of reclaimed water. No problem.
And this is our website. We keep all presentations, papers, reports on what we're doing on energy and water if you are interested.
One last question. Going once. All right. So, well, do you have a question?
Well, I just wanted to draw the audience's attention to the fact that a group known as the Western Resource Advocates, based in Denver, I think, issued a report a month or so ago on coal in the Southwest states. And they're talking about the tremendous implications of global warming from coal-burning power plants. And I think it would be advisable if you could take a look at that, as well as the audience, and if you just Google Western about a 16-page report, but it's basically designed to highlight the problems associated with projected coal-burning power plants in the Southwest, which of course use fresh water and also impact the air.
Okay, I will take a look at that. Thank you.
Okay, well, thank you very much. Thanks, Tom. Okay, so let's have lunch. Let's get back here at about 1:15, so we'll be just about 15 minutes late. That'll be fine.